point in time, without any further ado, because you've come here to listen to her, not to me, let me introduce Laura Parker. She does hail from the East Coast. She picked up her Bachelor's of Science degree there at Mount Allison University. Am I allowed to say in 2001? I have. Okay. However, she moved on to pick up her PhD from the University of Waterloo, and that was in 2005. And very quickly thereafter, she joined the faculty at McMaster University 2007 and has been there ever since. She is interested in observational cosmology and galaxy evolution, and this evening she's going to tell us about the wild side of the dark universe. Laura.
Thanks very much, Paul. So today I wanted to spend some time talking about cosmology, but from the perspective of an observer. So in astronomy, we kind of divide ourselves into people who study theory and people who use data from telescopes and are observers. So I'm going to explain some of the observational evidence that has led to our understanding of cosmology in the last couple of decades. So the first slide is my arrogant physicist slide, or astronomer slide, which is the cosmological pie diagram. So this is a picture of everything we have in the universe, and this is everything that everybody else studies. So this little piece of the pie here is all of chemistry, all of physics, all of biology, and actually almost all of astronomy. Everything that we can see, everything made up of atoms and molecules and everything we can study in the lab is this small piece of the pie. And the rest of the stuff in the universe is the so-called dark universe. So if I look at this a little bit more carefully, the universe is made up of a couple of major components. And so we have the mundane stuff, this little piece of the pie, and then we have two big components. The green part is going to be the focus of most of what I talk about tonight. This is dark matter. And the blue part of the pie is something we call dark energy, which was first discovered in 1998 and led to a Nobel Prize not too long after in 2011. And so at the moment, we have this remarkable picture, and it doesn't come from one kind of observation. It comes from a whole bunch. And so tonight I'm going to focus on the observations that led us to this remarkable discovery, that about a quarter of the stuff in the universe is some kind of matter that we can't see, that doesn't give off light, doesn't absorb light, but we can detect it through its gravity. And I'll give you some flavor towards the end of what this might be. And in terms of how we study this observationally, I like to think of this analogy of a jar of candy. And so this jar of candy is filled with dark candies, and let's imagine you can't see the black jelly beans. You can't see the black candies. And then we have the colorful ones. The colorful ones represent galaxies. Okay, so galaxies are going to be the focus of a lot of what I talk about tonight. And we can see the galaxies with our telescopes. We can't see the dark stuff. But you know the dark stuff is there based on how the colorful things are distributed. So if I took away all the black candy, the colored ones would just fall to the bottom of the jar. You can tell they are there by the distribution of the colorful ones. So you can figure out how many dark jelly beans there are and how they're distributed. And we actually do something really similar with galaxies. So I'm interested in these two components, this dark energy, which was discovered about 2 decades ago, which is actually causing the expansion of the universe to speed up. And I'm interested in particular in this dark matter that we can't see. And these two things together, actually, they kind of compete with each other. Dark matter, although we don't see it, acts like matter. And matter has mass, and mass gives us gravity. So this stuff behaves kind of like matter we're familiar with, that it has gravity. This stuff, we're not sure exactly what it is, but it's kind of like anti-gravity. It causes the expansion of the universe to speed up. And so the balance between these two things actually dictates what structure looks like in the universe. And so one of the ways to probe these two components is to study how structure changes over time. So the distribution of structure in the universe is sensitive to the balance between dark matter, which is gravity that makes stuff want to come together, like gravity likes to make things collapse, fighting against the dark energy, which makes the universe expand and makes things spread out. So these are snapshots from a simulation, and this particular simulation goes from early times in the universe on the left, all the way up to what the universe should look like on really large scales today. And exactly how the stuff in the universe is distributed will depend on the balance between dark matter and dark energy. So that's a simulation, that's very nice, but we want to measure this stuff. And so how do we measure it? We measure it by looking at the distribution of galaxies. And so if you're interested in galaxies, you want to look to the distant universe to see faraway galaxies. You first have to look out of our own galaxy. So we live within the Milky Way. Actually, I saw someone coming in tonight with a t-shirt that said, "You are here," with a picture of the Milky Way on it. So this is an artist's impression of our galaxy. And we live about 2/3 of the way out from the center. Here's the location of the sun in this schematic picture of our galaxy. So looking at our galaxy in one way, it looks really big. But because our galaxy is quite flat, it's big in one direction and very flat the other way. And this is an advantage for someone like me who studies distant galaxies. And the reason is, if you look within the plane of our galaxy, you just see stuff in the Milky Way. But if you look out of the plane, above or below, then you look to darker patches of the sky, you can see beyond the Milky Way to the distant universe. So if you want to study faraway galaxies, you look away from the Milky Way. And if you're really, really lucky and you have access to something like the Hubble Space Telescope, you point at one of these dark patches of the sky, far away from where most of the Milky Way light is, and you open the shutter on the camera. And you open the shutter on the camera for days upon days upon days. So this particular snapshot I'm going to show you came from an exposure that was taken over the course of 20 days or so. So you have a little patch of the sky, you point at it with the Hubble Space Telescope for day after day after day. And it's much smaller than the size of the full moon, just for scale. So if you do that, you get an image like this. Some of you may have seen these kind of images before. There's been a series of them: the Hubble Deep Field, the Hubble Ultra Deep Field, the Hubble Extreme Deep Field. But they're all the same idea. You take a dark patch of sky and you point the Hubble Space Telescope at it for a long time. And people like me get incredibly excited by images like this. In this one image, you actually have thousands of galaxies. Every spot of light you see, from the tiniest little smudge to these big things, other than these spiky objects, there are 3, 1, 2, and there's another, there we go, 3. Those are 3 stars in our own Milky Way. So if I go back to this picture, even though we're looking away from the plane of the galaxy, there will still be a few Milky Way stars that annoyingly get into your image. Okay? So for me, if you study stars, fantastic, that's great. I study faraway galaxies, and so for me, these are annoying objects, and you can't escape it. So you get this field of view with 3 stars and a whole lot of galaxies. And it might help if I zoom in just so you can see the kind of beautiful images we get with the Hubble Space Telescope. Every smudge you see there is real, and it's a galaxy. Every one. So I'll show you another patch of sky here. Every single smudge is a galaxy. And those galaxies have, on average, about 100 billion stars each. And as we've started to learn, just by looking at our own little neighborhood of stars around the sun in the Milky Way, at least about half of stars have planets. So if that holds true in these other galaxies, then that means that what you're looking at here is actually hundreds of billions of planets. And these are almost certainly, some of them will be very much like Earth and we have a high probability in an image like this that we're looking at life out there in the universe. And I find that amazing when you stare at these images. But for our purposes today, why galaxies are exciting is they're the colored jelly beans. Okay? So where these galaxies are and how far apart they are and how they move in the universe can tell us about the dark stuff that we can't see. Okay? So today I really wanted to focus on the one part of the cosmological pie diagram, which is the dark matter. And the reason for that is this is closer to my area of expertise. I spent my PhD and some years afterwards primarily working on this third technique here called gravitational lensing. So I'm going to go through a few different ways that we've come to learn that the universe is filled with this stuff called dark matter. And I should point out that this list of 3 here is not exhaustive. We actually have a whole bunch of other tools as well for measuring how much dark matter is in the universe. And what's been incredible in my time as an astronomer is that this piece of the pie went from having a huge uncertainty for how big it is. I get very animated. A huge uncertainty in how large that piece of the pie is, to us now having many techniques that all come to the same conclusion. Totally independent ways of measuring how much stuff is in the universe, and they all agree, which is amazing. And in fact, I think your next speaker, or sometime soon in the series, you have Mike Fick, who's coming from the University of Waterloo, and he's going to also talk about cosmology and cosmological parameters. Okay. So the first technique I want to talk about actually goes all the way back to the 1930s. So this is a false color image of the Coma cluster, which is a cluster of galaxies. So hundreds of galaxies all bound together by gravity, all orbiting around each other. And this system was studied by an astronomer named Fritz Zwicky. And every picture you find of Fritz Zwicky on Google Images, he looks like a character, and all the stories I've ever heard, it seems like he was a character. So he was a Swiss-American astronomer based primarily at Caltech. And what he studied was the motions of galaxies within the Coma cluster. This is a simulation. We can't actually see the galaxies moving around like that in real time. But what you can do is measure, so this is now a cartoon version of the Coma cluster. You can see all the galaxies and measure, compared to the center of the cluster, are the galaxies moving away from us, which is denoted by a red arrow, or towards us, denoted by a blue arrow. So he measured how the galaxies were moving along the line of sight, towards us or away from us, and how fast are they moving. And there's some lovely simple physics that tells us if you can measure how fast things are moving within some spherical distribution like a galaxy cluster, you can tell how much mass is in that system. And you can think about it, if the galaxies are moving at really high speeds, then unless there's a whole lot of mass there and a whole lot of gravity in that cluster, the galaxies will just fly off into space. And what Zwicky amazingly measured in the 1930s is that they were moving really fast. And the only way for the cluster to stay together, to stay stable over time, is if there's a whole bunch of mass there that we can't see. And so this was the origin of dark matter, but I would say pretty much ignored until some other important observations came along in the 1970s. So starting from the very end of the 1960s into the early 1970s, important work by a few astronomers, but really led by Vera Rubin, measured how fast the stars are rotating within individual galaxies. So Zwicky looked at the motions of a bunch of galaxies within a cluster of galaxies. What Vera Rubin and collaborators did was focus on the motions of stars within individual galaxies, or even the motion of gas within galaxies. And so similar physics applies that how fast a star is orbiting around the center of a galaxy is sensitive to how much mass is in that galaxy. And when you set out to do these measurements, you don't necessarily know what you'll find, but in galaxy after galaxy, what's discovered is that the stars in the galaxy are orbiting really fast. And that implies that the galaxy has more mass than we can see. So just to point out, before I show you how this works a little more, Vera Rubin is a personal hero of mine. I've worked in dark matter-related astronomy since I started, and I was interested in this since I was an undergrad. And I had the chance a couple of times to meet Vera during my earlier career. This is a picture from a conference at Queen's 9 years ago, where it was in celebration of Vera Rubin's 80th birthday. And so this is her, this is me. She's a hero. I get as close as I can to my heroes. And I just want to point out that one of the great tragedies, in my opinion, of 20th century, 21st century astronomy and physics is that Vera Rubin, for this pioneering work, was not awarded a Nobel Prize in physics, and you cannot be awarded a prize after you pass away, and Vera Rubin passed away on Christmas Day in 2016. So to date, there have only been 2 women who have ever won the Nobel Prize in physics, and there hasn't been one for decades. And so this was, I think, a clear oversight on behalf of the Nobel Committee. So getting back to what Vera did, she measured the speeds of stars or the speeds of gas around the centers of galaxies. And this is a simulation view now of 2 galaxies. The one on the left has no dark matter. So everything that's in that galaxy is the stuff you can see. On the right, we have a galaxy that has dark matter. And the big difference is how quickly the stars are orbiting around the center of the galaxy. And I think if you stare at these long enough, you can convince yourself that you can see this, that on the left, as you go out to the outskirts of the galaxy, the stars are orbiting more slowly than on the right. So on the right, the stars on the outside are orbiting at the same speed as the stars on the inside. And we can show this also in a graphical form, where on the below the 2 videos, there are plots showing how fast the stars are rotating versus how far away they are from the center. And a galaxy without dark matter shows this characteristic decline, that as you go to large distances, the stars are orbiting more slowly. And on the right, a galaxy with dark matter, the velocity, the speed of how fast the stars are rotating is constant with radius. So what Vera Rubin and others were finding in the 70s is that galaxy after galaxy after galaxy looked like this, which implied that there was extra mass that we can't see. So this was a really revolutionary measurement. And I think if you have a hard time picturing the rotation curve, sometimes it's nice to think about an analogy. So this is the rotation curve. I plotted it this morning for our solar system. So this is the speed, the same as the plot on the previous slide. The speed at which, now instead of stars, it's the planets in our solar system. The speed at which they rotate compared to how far away they are from the sun. Okay? And what you can see is there's clear characteristic declining shape. That if you're close to the sun, you orbit really fast. And as you get far away, the rotation speed goes down. This is what it looks like for a system where the mass is in the middle. So in our solar system, 99% of the mass of the solar system is in the sun. So if most of the mass is in the center, then as you go out from the center, the rotation speed will decline, and it will follow this shape. And one might naively expect the rotation curve of galaxies to kind of look like that. So if I show you a picture of an edge-on galaxy, so instead of the big view, we're looking at it edge-on, you see that most of the light is in the center. Galaxies are much brighter in the center, and there's a lot less stuff as you go out to the outskirts. So naively, you might expect the rotation curve for a galaxy to look somewhat like the rotation curve for our solar system. But that is not what was found. What was found instead is that the rotation speed is constant with radius. It doesn't decline. And so there must be mass in galaxies that we can't see. And just to show a picture of this, of real data, so scientific data for a galaxy in the nearby universe, this is that same plot again, how fast you're rotating versus radius. And if you add up all the luminous stuff, the green is what you would expect for the rotation curve. So you add up all the stars, all the gas, everything you can see. What would you expect if the only thing that was in that galaxy was the stuff you can see, and you know how massive that all is? What would you expect for the rotation curve? And that gives you the green. But what's measured, and measured with great accuracy here, are these black points with little tiny error bars. And you can see that's remarkably flat. So over a huge range in radius, this galaxy is rotating at a constant speed. And the difference between the data and the expectation based on only luminous stuff is what we call the dark matter component of galaxies. Okay? So if you add in some smooth component of dark matter, you can match the observations. So it's perhaps indirect, but it's convincing in that galaxy after galaxy after galaxy shows this same rotation curve. And amazingly, the amount of dark matter you need to explain that is consistent with a whole bunch of other ways we now have of measuring dark matter in the universe. So the third one I wanted to spend some time talking about, which is one of my areas of expertise, is using the tool of gravitational lensing. So if you think back to when you first learned about gravity, you learned that the amount of gravity depends on the distance between two masses and how massive they are. So the further apart things are, the more the gravity goes down. The more massive they are, the more gravity there is between them. So that was our classical picture of gravity. That's what we get from Newton. Einstein revolutionized this about just over 100 years ago with his theory of general relativity, where he describes gravity as being a geometric effect, where when you have masses distort the fabric of space-time around them. And I know that sounds crazy, but this idea of general relativity makes some really fundamental predictions. And one of those predictions is that although we know in classical gravity, two masses feel gravity between each other, in Einstein's gravity, even light feels gravity. So light has no mass, but light is affected by gravity if gravity is the curvature of space-time. And so the picture is that if you have some background object giving off light, as it travels through the universe in a straight line, if it gets close to some massive object, it will actually feel the gravity of that object and change its direction. And Einstein predicted this would happen, but he didn't think it would really be practical to measure it. And the reason is that the size of the effect, how strong is this deflection of light as it goes around a massive object, depends on how massive the object is. And the expectation for how much the light would be bent by stars is in the units of micro arc seconds. And so if you don't know what that is, that's because it's so small, you've never experienced an angle so small. So 1 arc second is 1 divided by 3,600 degrees, okay? So it's a tiny, tiny fraction of a degree. And then we're talking about micro arc seconds. And so this is a ridiculously small angle that we don't experience in our everyday lives. But if you start to think about more massive objects causing this effect, galaxies, we start to get into deflections, the amount that the light gets bent, of 1 to 2 arc seconds. This is actually something that the best telescopes on the best sites can start to resolve, can start to see. And if you talk about even more massive objects causing lensing, like galaxy clusters, then we get into a regime that we can measure, okay? So just another schematic here. If you have a cluster of galaxies, and you're here with your telescope on Earth, light from background objects, as it passes by this cluster along the line of sight to you, the light will be bent, and it will cause big distortions, and it should be measurable if this mass is big enough. And so this was a fundamental prediction of Einstein's theory, and it's now something that we use as an almost everyday tool, which is amazing, which really wasn't possible until the 1990s or so to use this tool. And so to show you that it's real, here's a beautiful image taken by the Hubble Space Telescope. And what you see here in the orangey color, these are all galaxies in a galaxy cluster. So these galaxies are all bound together by gravity, orbiting around each other. They're one big system of galaxies. But what is striking about this image is not the big fuzzy orange galaxies, it's these long arc-like, some of them almost linear, these arc-like features. Those don't look like normal galaxies. Galaxies don't look like big stretched out lines. These objects that you're seeing are actually background galaxies way behind the cluster that as their light travels through the universe, because it comes close to this cluster along the line of sight to us, the light gets distorted. So if we go back to this picture, we're looking at distant galaxies whose light has been distorted by the galaxy cluster. And in fact, sometimes more than one ray of light can reach us from that galaxy from different directions. And so in fact, some of these arcs will have an arc on one side of the galaxy and an arc on the other side of this galaxy cluster can actually be the same background galaxy. The same object in 2 places on the sky. And Newton did not predict that. So this is something that is special from general relativity, and it's something that has been confirmed, and we use all the time as a tool. So these are the most dramatic lensing diagrams, these pictures of beautiful clusters, but individual galaxies can also cause the lensing of a background galaxy. So in these pictures, we have 8 thumbnails of orangey, big orange galaxies. These are elliptical galaxies that are along the line of sight to some background galaxy. And the background galaxy is blue. And the background galaxy lives almost exactly behind this elliptical orange fuzzy blob. And as the light from this background galaxy approaches this elliptical orange fuzzy blob, it actually goes around it and makes a perfect circle. So we call these things Einstein rings. A background galaxy, which should look like that, is instead distorted into a ring on the sky, which is amazing, right? It's amazing that nature does this to us. But what's so great about this as a tool, if you're interested in dark matter, is what's causing the lensing is the mass of this system. So if you calculate how much mass is in the stuff you can see, you wouldn't get that much lensing. The only way to get this much lensing, either from galaxies or from galaxy clusters, is if they're filled with dark matter. If most of the mass in these systems is stuff you can't see, then it's consistent with causing these big arcs. If everything that you see in this picture, if that's all that there is, you would not have this strong gravitational lensing effect. Okay? So these are dramatic, beautiful images, and I'd like to say that I got to work on these during my PhD, but I actually did something a little bit harder. And that is a regime that we call weak lensing. So what I just showed you is something called strong lensing. You take a picture, you can see that something is up. It's not normal to have a galaxy in the shape of a ring on the sky. There's something pretty dramatic there. That only happens when your background source of light, your lens along the line of sight, and you sitting at your telescope, if you're all in a nice line. So if everything's perfectly lined up, then you get this really strong lensing. And so in this simulated image, this is a real image of galaxies that's been artificially distorted by a lensing signal. And so what's happening here is in the lower left-hand corner, a big mass was assumed to be along the line of sight, and then the lensing signal was simulated around that mass. And here, you can tell with your eyes, there's something going on in that corner with the background galaxies. You see it. That's the strong lensing regime, so you can see that in your image right away. But if you go far away from this heavy mass that's causing the lensing, you go to galaxies in the background that are not right along the line of sight, that are further away. You get to this little region here, which is blown up on the right. These galaxies actually look kind of normal. So if you take a grayscale image of distant galaxies, that's what they look like. So you don't get all that beautiful detail of some of the HST images. This is a typical ground-based image taken from a good telescope somewhere on Earth. These galaxies don't look like there's any lensing going on. But if you can carefully measure the shapes of all of those galaxies and measure how they're aligned, you'll find something interesting. So if you have enough galaxies on the sky, and if there was no lensing effect at all, then you take a bunch of things that are kind of elliptical and you have them randomly on the sky. The average shape should be a circle. So the average shape of a whole bunch of ellipses will be a circle. If, on the other hand, you have lensing, then the average shape of these galaxies will not be a circle. It will actually be an ellipse, which is aligned in the direction of that red line. If we go back over here, that direction is a tangent to this mass. And so what happens in the regime of weak lensing is you don't see multiple arcs on the sky. There's nothing dramatic. But if you can carefully measure the shapes of lots of galaxies, you'll find that they're actually a little bit stretched out tangentially to a mass. And if you can measure that really precisely, you can figure out how much mass there is there, how much dark matter there is. So in the strong lensing regime, we can measure the mass causing the lensing on these kind of scales. With weak lensing, we can measure how much mass is in this whole area. And that's the power of weak lensing. It's hard because it's not dramatic. You don't just see it in the pictures. It's really hard. But it allows you to measure the masses on really large scales. And just to give you a feeling for what this is really like, just so I can convince you that my job wasn't easy, this is a nice image from the CFHT, the Canada, France, Hawaii telescope, which I'll show you in a second. These are the kind of galaxies I'm talking about. So we're measuring the shapes of those. And so measuring the shape of one of those is not going to tell you very much information. It's averaging the shapes of many, many, many galaxies over a huge region that allows us to build up a signal. So just to emphasize again what happens in the real world, not in some idealized simulation, you have a galaxy which is, here it's a Hubble Space Telescope galaxy, beautifully resolved. You lens it. This is highly exaggerated, how much the lensing effect would change the shape. It's really about a 1% change in the shape, which you wouldn't be able to detect. So here it's exaggerated. And then you look at it through the Earth's atmosphere, which blurs everything out. And then you have a digital camera, which has a finite scale of pixels. And then you have noise. So we're measuring the shapes of things like this. But the universe is kind to us in that there are lots of galaxies. So the measurement of one doesn't tell us a lot of information. But the measurement of thousands of galaxies allows us to map the shapes of galaxies across the sky and figure out how much mass is between us and those galaxies. So we have, in Canada, we're really lucky because we have the premier facility to do these kinds of observations. This is the Canada, France, Hawaii telescope on top of Mauna Kea. That's me. This is the other telescope, big telescope that Canada is a partner in terms of optical telescopes on Mauna Kea. This is the Gemini telescope. There's a twin to it in Chile. But CFHT has been there since the 1970s. And it's getting a bit dated. It's only a 3.6 meter telescope. This one is 8 meters across. So 3.6 meters across is a lot smaller. It doesn't collect quite as much light. But it turns out that this location on the summit has the absolute best conditions for imaging, for taking pictures. And so the images we get from CFHT allow us to do this kind of work better than almost any other place on Earth. So Mauna Kea is a really special location to do really high quality imaging. Hubble is nice, but Hubble has a very small field of view. So you measure this tiny little field of view with the Hubble Space Telescope. So if you wanted to do a big area, it would take you a very long time, and you'd be unlikely to get enough time with Hubble. With the Canada, France, Hawaii telescope, we get 1 square degree at a time, which in astronomy terms is actually really big. So what we've learned from doing this kind of work is that galaxies are not the things that we see. The stars and the gas that we can observe with telescopes are a small fraction of what's out there. So through measurements, particularly from lensing, we've learned that the galaxies live in these big extended objects called dark matter halos. So every time you see a galaxy like this, a beautiful picture, I want you to picture that. So galaxies actually are much larger than the extent that we see in the images. They're embedded in much larger structures. And we can measure how big these dark matter halos are around galaxies and exactly how the mass is distributed by using gravitational lensing as a tool. And I showed you that we can measure the lensing to measure the masses of galaxies in these dark matter halos, but we can also do this on very large scales. So if you take some background galaxies in the universe, and you watch as their light travels through, this is the large-scale structure of our universe, all the way to us on the right-hand side, the light will be deflected along the way as it passes by the large-scale structure in the universe. So if you take really distant galaxies, their light will actually follow an interesting path through the universe. It'll be lensed multiple times. And we have some tools to try to measure this effect. And that will allow us to measure the mass in the universe on really big scales. So just a reminder that when we're looking at distant galaxies, we're actually looking back in time. And so when we look at really distant galaxies, any patch of sky, we're seeing galaxies that are maybe 1 billion years ago, 2 billion, 3 billion, 4 billion. In a flat image, we actually have galaxies at all different distances. And we're looking back to different epochs in the history of the universe. And if we measure the lensing signal of galaxies in each one of these slices, take all the galaxies at one distance, measure how much lensing they have, all the galaxies at another distance, measure how much lensing there is, we can actually start to make a map of all the mass in the universe in that part of the universe. So this was done for the first time with a small field of view from the Hubble Space Telescope, and now it's being repeated with much larger surveys from the ground. So this is a map of mass in the universe from today, which we talk in cosmology, we call that redshift of 0, but this is today. This is 7 billion years ago. So we're looking out to really big distances. And in this little tiny patch of the sky, the field of view that the Hubble Space Telescope can see, that's the mass in that part of the universe. And by tracing out how the mass is distributed, whether there's big holes, how dense the stuff is in the universe over time, we can actually start to measure the balance between dark matter, which likes to make things collapse, and dark energy that likes to make things expand. So we're doing this kind of mapping now on much larger scales. So I just wanted to say a few words to finish up about what the dark matter might be. And so when I started in this field, this was the debate. Is dark matter wimps or machos? And I can't really show this in class anymore because, well, this is not politically correct, probably. And people don't know who this is anymore.
No.
Macho Man, Randy Macho Man Savage, a wrestler from the 80s and 90s. So it's not a reference that everybody gets, but it helps with the wimps versus machos. So let's put this in more physical terms now. So when I say wimps versus machos, the debate for what this dark matter could be. So by the time the 80s and 90s had come around, people had started to believe Zwicky's measurements of how fast galaxies move around in clusters. We had Vera Rubin's measurements. We were just starting to do gravitational lensing. And the question is, if there's all this stuff out there that has mass, but we can't see it, what is it? And the two real theories that were being debated were, is the dark matter some kind of particle that hasn't been detected yet? Or is it something more mundane, like black holes? That's a joke, because black holes aren't that mundane, but things that we know exist already, macroscopic things, like dim stars, asteroids, planets, things that are not very bright, black holes. Could there be enough of those dim things in the universe to explain the dark matter? And the bottom line is, I won't go through all of the history on this today, but it's absolutely for sure that it's not these macroscopic things. We have careful ways of looking for those. It's not that. And so we're left with the best explanation that actually fits all the observations we have to date, is that there's some particle we have not yet detected. And in the early days, one possibility for that particle was neutrinos. But now we've actually measured the properties of neutrinos we actually understand some of the properties of neutrinos. We know that that can't be the dark matter. And so we're looking for these. And so this is a huge experimental effort, and this is not my field. I'm an astronomer. But there are these projects all over the world to try to find these weakly interacting massive particles. That's what WIMP stands for. And there is no lack of possibilities from theory, and the goal is to try to find them in the lab. And there's two ways to try to find them. One is to have a WIMP interact with some material in a way that you can measure it. Now, it turns out we're made up of atoms and molecules. Atoms and molecules are mostly empty space. You've got these little tiny atomic nuclei, and then you've got these huge electron clouds, the electrons whizzing around. Most of space is empty. And so these particles, these WIMP particles, don't interact with light, they don't interact with electrons, but every once in a while, even though space is almost empty, a WIMP could directly collide with the nucleus of an atom. And if you have a way of detecting that, what's called a nuclear recoil, you can actually maybe detect the WIMPs. So this is the kind of work that's happening now in Sudbury. So you've probably all heard of the Sudbury Neutrino Observatory, and there was a display on the way in with a picture of Art McDonald celebrating the amazing achievements of the Sudbury Neutrino Observatory, which led to a Nobel Prize. That lab has now been largely turned over to looking for dark matter. So in Sudbury, they still do neutrino experiments, but they also do experiments to try to find dark matter. So they're looking for this. In parallel, people are looking at high-speed collisions at the Large Hadron Collider, the border between Switzerland and France. At a high-energy collider, when you have these high-energy collisions, every particle that has the energy of that collision and less, so a mass that corresponds to that energy through E equals mc squared, every particle that has that energy or less will be created in these collisions. And so maybe they'll make dark matter. And I love this cartoon. It's made by CERN, so they're making fun of themselves. We have these physicists looking at a screen, and they say, do you think it's a neutralino? No, I'd say it's a gravitino. No, a neutrino. And someone else says, it looks to me just like spit. These three are all candidates for dark matter particles. So when I say we're looking for these, we're looking very hard, but at the moment, it's the experiments that need to catch up with the theory. So from theoretical physics, there's a whole bunch of things that might explain dark matter. Now we need to find it in the lab. So at the moment, if we're right, and if the universe is filled with WIMPs, then as the Earth goes around the sun and the sun goes around the Milky Way, we're moving through a sea of these in our own galaxy all the time. So at this instant, you have millions to billions of these streaming through your body. It doesn't bother you, it bothers her a little bit. But if she finds them in the lab, if you manage to detect them, then you get to go to Stockholm and pick up your Nobel Prize. This would be revolutionary to find these in the lab. And so today, I didn't get to tell you the story of dark energy, although I'm happy to take any questions on that. So we talked about this piece of the pie, dark matter. We didn't get a chance to talk about dark energy, so I'll just tell you one thing about it. And that one thing is that this is our cosmological pie today. So today, dark energy is the most important thing in the universe. But all of our observations to date are consistent with dark energy being something we call a cosmological constant. What that means is that if we look at the stuff in the universe, the density of dark energy has never changed. It's just this constant value. Whereas everything else in the universe gets diluted as the universe gets bigger. This is our intuition, right? You have a bunch of particles in a volume, you make the volume bigger, then those particles are going to spread out, and the density of particles is going to go down. So everything we experience in everyday life says that as the universe gets bigger, stuff should become more diluted. The density should go down. Dark energy is bizarre. You make more space, you make more dark energy. So as the universe gets bigger, you make more dark energy because it has a constant density everywhere we look. So what that means is that today, dark energy is the most important component of the universe, but in the past, it wasn't. And what that means for the history of the expansion of our universe, what it means is that early times, matter was the most important thing. So we have the Big Bang, the universe is expanding, but the expansion rate is slowing down because all the gravity from all the matter is dominating. So the expansion actually slows down. And then sometime, when dark energy becomes the most important thing, the universe starts to expand, to accelerate in its expansion. So that's the current state of our understanding. The question is, what is this component? And so that's where the next generation of experiments is going. So this is our universe today. This is the cosmological pie. So all the normal stuff, all this dark matter, and then all this dark energy. But in the future, if the observations are consistent with, if everything continues on the way that it is, this is what we expect the future to look like, a universe dominated by dark energy. So what does that mean? The universe is expanding, and the expansion is accelerating. It actually means that in the distant future, if you look up at the night sky, galaxies that we can see today, astronomers in the future would not be able to see. As the universe expands, galaxies will actually disappear from view. The space will just get too big between us. And so in the future, if there are some civilization on some planet, on one of those galaxies I showed you in that first beautiful image from the Hubble Space Telescope, they might not be able to take a picture like that, or see all these other galaxies, or figure out that they live in a universe filled with dark matter and dark energy. We use galaxies to figure out this picture. If the only galaxy you can see is the one you live in, you would not be able to figure out that this is your universe. So I feel sorry for these astronomers, and I feel fortunate to be here. So the picture I want to leave you with, again, is this analogy that galaxies allow us to trace out structure in the universe, and it really is an amazing accomplishment to have this picture. We have a whole bunch of independent measurements. I have not told you half of them today. We've got the cosmic microwave background. We have these things called baryon acoustic oscillations. We have a whole bunch of ways of measuring what this pie diagram looks like, and within a couple of percent, they all agree. This is what the stuff in the universe looks like. This is the distribution of stuff in the universe. So amazing accomplishment, but also a lot of work to be done. We still don't know whether this really is WIMPs and what those WIMPs might be, and we certainly don't know what is this weird stuff that every unit of volume in the universe has some constant density of dark energy. And so whoever figures out those questions is guaranteed to get a Nobel Prize. And I'll stop there.
Yes, I now know why I don't like black jelly beans. And I do like stars. At any rate, lots of good thoughts there. So questions to ponder and ask Laura. We have a question from the website.
Microphone.
Question from online. As the universe expands and more dark energy is needed to fill the space, does that mean it's diluted or over time, or is it made up somehow?
So to the best of our understanding at the moment, if it truly is a cosmological constant, it means more space, more dark energy. So for every unit of space you create a new amount of dark energy. And so that could mean that empty space has some ground level of energy. So you have more space, you have more energy.
Great talk, thank you. In your diagram showing the rotation of the mass in the galaxy, it seemed like there was an inverse relationship between the visible matter and the dark matter. Is there can you comment on the fact that dark matter doesn't like visible matter, or do they not want to occupy the same space?
No, it's a good question. And in fact, both dark matter and visible matter have higher densities in the middle of galaxies, and they fall off. But what happens at large radii is the dark matter becomes more prevalent than the luminous matter. And there's actually a really good reason for that, and it's some nice physics. So dark matter, our definition of dark matter, we don't know precisely what it is, but we know it doesn't interact with light, because we would just see it otherwise. It doesn't absorb light, doesn't give off light. And what that means is that if you've got a big ball, when a galaxy forms, let's say you've got a big ball of dark matter, and in that you've got a bunch of regular matter, and you're going to make a galaxy in the middle of that. What happens? The regular matter starts to collapse under gravity, and in order to get down to the middle, it actually radiates away energy with light. The dark matter is there, and it would like to collapse under gravity, but it has no way to shrink to smaller size because it can't radiate away energy, which is what you would have to do to become more compact. So the dark matter stays fluffy and big, and the luminous matter sinks to the middle of the potential because it can give off radiation and shrink to a smaller size. Yeah.
Thank you for a great explanation. Is the sound working?
Yeah, perfect.
Thank you for the great explanation of the speeds and everything, and there's something weird happening. How strong is the evidence that it's dark matter as distinct from a totally different theory of gravity that might work.
Okay, so I had a slide on that I deleted. So, since you asked me though, apologies. Okay. So 2 possibilities. We have, it doesn't let me do that. Okay, we're gonna look at it like this. So there are 2 possibilities for what the dark matter, what these observations could mean. We see for sure the stars are orbiting fast at large radii. So does that mean that there's dark matter, or does it mean we don't understand gravity? Those are the 2 possibilities, because saying that a rotation speed tells us the mass means we're using some law of gravity to go from velocity to mass. So there's an alternative theory, which I would say probably 2% of astronomers seriously consider. And it's a theory called modified Newtonian dynamics. Basically, instead of gravity being GR, we have a different theory, general relativity, we have a different theory of gravity. And through changing Newton's law a little bit, changing Newton's gravity a little bit, you can actually explain the rotation curves. So you can come up with an alternative explanation that works for the rotation curves. But that explanation does not explain the clusters, the lensing, the cosmic microwave background, or any of the other measurements. So there's no one theory that can consistently explain everything except for particle dark matter. So you can explain rotation curves. So this is an example from a paper where we have rotation curve versus radius, and the data points are the measurements, and the modified gravity theory is in blue, and it does a beautiful job of reproducing. So modified gravity is one explanation that people like to consider, but it just can't explain all of the observations.
I have 2 questions. Hopefully they're pretty short. One, in your pie diagram, like what units are we comparing there? Because the 3 things are so different. Is it mass energy or, like,
Yeah.
you got me?
It's mass energy, exactly.
Okay.
Yeah. So it's the proportion of mass energy, to be technical. Yeah.
Okay. And the other question is the dark matter halos, do they have a relationship to the size of the galaxy? And in a galaxy cluster, is it like a homogeneous soup, or are they still pretty distinct for each galaxy?
Such a good question, and I struggled with trying to answer that for 2 years, observationally. So in answer to your first question, the size of the dark matter halos scales with the size of the visible galaxy. So a bigger visible galaxy lives in a bigger dark matter halo. So that's a very nice correlation that we've measured well. Inside a big galaxy cluster, now you've got a whole bunch of individual galaxies. There's one big dark matter halo and a bunch of galaxies within that dark matter halo, but each galaxy hangs on to a little bit of its dark matter. But the longer it's in the cluster, the more of its own dark matter it loses to the big overall thing. But one of the big questions we're trying to answer is how quickly, so imagine you have a galaxy cluster and you have a galaxy outside of it that falls in. So this happens all the time as the universe evolves. The galaxy falls in. How quickly does it lose its dark matter to the cluster dark matter halo? That's a question I have a PhD student working on right now. So that's not an answered question.
I want to go on something I think I picked up close to the beginning of your talk. On all the books I've read from the 80s, 90s probably, they talk about, there's this question about whether the expansion universe is increasing or decreasing. If it's an open universe or closed. Has that been answered?
Yeah. So this cosmological pie diagram gives us our answer. So I started out learning, when I started out learning cosmology, the big question was, okay, our universe is expanding today, but if there's enough stuff in the universe, enough matter in the universe, you would think maybe the universe could expand and then turn around and collapse. Or if there's not enough stuff in the universe and not enough gravity, it'll just expand forever. So that would be an open universe, and the one that recollapses would be a closed. Dark energy throws a huge wrench into that simple picture, because now we're not just trying to balance expansion versus gravity. We've got expansion and then extra energy from dark energy outwards and gravity inwards. So because we have this extra feature of dark energy, the universe is open. Well, the universe is actually geometrically flat, but it's going to expand forever. Yeah.
Another. Lost my feed just a second.
There's also someone way at the back who's had their hand up as well, just for after.
Sorry about that. Question from the stream. What are the best likely candidates for dark matter, and what candidates have been ruled out by current or past experiments?
So the most important ones that have been ruled out, first of all, would be neutrinos. So if you have a particle that has too low a mass, it doesn't clump together well to make dark matter halos. So we can rule out a whole bunch of particles whose masses are too low. So if you're too low a mass, you move around too fast and you can't clump together. So those are ruled out. Of the remaining ones, there are particles that are suggested from a theory called supersymmetry. And those are the ones that start with in that picture, so neutrinos. So anything starts with an S. And so far, we would have thought perhaps that the Large Hadron Collider would have seen evidence for the existence of supersymmetry, and it has not. So I think some of those supersymmetric particles are starting to become not so favored. There's another particle that a lot of people have researched, something called an axion. And axions have some promising characteristics, but this is definitely not my forte.
At the beginning you mentioned Fritz. Is he the guy that is the first person to come across dark matter?
Yeah, so in retrospect, yes. So he is the person who measured these motions of galaxies in clusters. And he actually it was also named in German, Dunkelmaterie. So there's a paper from 1933 which calls it basically dark matter in German.
Okay, but so before Fritz, your cosmological pie chart was it the blue part or green part? The little sliver.
Yeah,
was the pie chart.
That's right.
So how do we know that there isn't another slice of the pie that we just haven't observed yet? Is there something else? Is there the possibility of something else?
It's hard. Now it would be hard because what we now know is the total of all the mass energy of the universe. We know that really well. And we can measure those different components. And those different components add up to the total we expect. So they didn't know that at the time. What's the total mass energy of the universe? We now know how much stuff goes into that whole pie diagram, and we measure the pie components. And so it's very unlikely, although of course sometimes nature surprises us, but we have the total correct, and then we know all the components that add up to the total. So I think we're on solid footing now. I should mention that this is remarkable that this was done in the 1930s, because you go back only a decade before, and we didn't know that galaxies were outside the Milky Way. We were still arguing about what the nebulae were, the fuzzy things in the sky. And so to go in such a short period of time from not being sure about whether there are other galaxies to Hubble measuring the expansion of the universe and then Zwicky measuring the motions within the Coma cluster. So a lot of progress really, really quickly.
This may be a little off the wall, but there was an experiment done many years ago around the same time, I believe, as Zwicky, where they beamed radiation at 2 gates, and they found diffraction of particles. Mm-hmm. So the question was, are particles waves or are particles particles?
Yep.
So has anyone considered the fact that this dark energy or dark matter, may be waves of some sort?
Well, the amazing thing about quantum mechanics is every particle is a wave. So, and the lower mass you are, the more wave-like you are. So when these experiments with 2 slits, where you have particles that can diffract, that only really works well for very lightweight things. So as you go to more massive particles, the wave-like behavior gets suppressed, and they behave more like ping-pong balls. So depending on the mass of the dark matter particle, if it's at the low mass end, it will have a little bit more wave-like properties, the high mass end a little bit less. But I think that's something that's well understood. It just depends on how massive the particle is. Yeah. But that's an awesome experiment.
Sorry, there's an observed diffusion of dark matter out of individual galaxies into the galaxy clusters.
Yep.
Is that contributing to the accretion of the supermassive black holes at the center of galaxies?
Indirectly. So every big galaxy has a supermassive black hole at the center. This is another remarkable discovery of the last couple of decades. And in order to grow the black holes, you need to funnel material down to a very small radius. And the best way to do that is through interactions of multiple galaxies. But it turns out that clusters, the galaxies are moving around so fast that they have such fast encounters, they don't merge well. They just fly by each other. So actually, galaxy clusters are not the best environment in which to grow supermassive black holes, but the merger of two galaxies is a great way to have a slow interaction that sends a lot of material to the center of the merging system. And the only reason why they have such a strong interaction gravitationally is because they have so much dark matter. So they've got a lot of mass, they're really attracted to each other. So pairs of galaxies are a really good way to grow supermassive black holes, but not the clusters.
Question on dark energy.
Yeah.
So you said the universe is accelerating if there is a dark energy. How do you come up with that? Like basically in terms of redshift, you find the speed, right? And it works against that. How do you calibrate that?
So the original measurements that convinced the world that this existed and led to the Nobel Prize were using these special objects called Type 1a supernovae. So this is a galaxy, and this is a supernova that's exploding in that galaxy. There's a special kind of supernova that always has the same brightness. We call those things standard candles, and they're lovely because it's like I'm holding a 100-watt light bulb. And as I back up, it's going to look fainter to you. So you can tell how far away I am just by how bright that 100-watt light bulb appears. And so for these kinds of supernovae, we have this measurement of distance, standard candle measurement of distance, and we have redshift. So we have two ways of getting their distance, and these two ways don't agree with each other. And the further away a supernova is, the more they disagree. And the way to reconcile the two distances is actually if the universe has expanded more since the light was emitted than it would have if there weren't dark energy. So that was the original measurement made in 1998 by two independent teams. And those two teams actually disagreed with each other about how to do the analysis. They came to exactly the same conclusion, and both teams won the Nobel Prize. So the supernova were the way this was first measured, but now we also measure it with lensing. So if you have more dark energy, then the mass in the universe is being more spread out in time. And so you can measure the growth of structure. How spread out is all the mass in the universe becoming as the universe expands? We can measure that.
Going back to that,
You're good.
the Hubble Deep Field photos, I've always wondered, can you tell the distance of each of those little dots or galaxies by, like, is that what color? Like the redder ones would be further away?
If only it were so simple.
Pardon?
If only it were so simple. So
I meant relative.
Yeah. So the color, it's true that as galaxies get further away, their light becomes redshifted. So what that means is that the light they're giving off, because the universe is expanding, the waves of light get stretched out and they look redder. But the colors we see of galaxies are not just due to their distance. There's intrinsic properties of the stars within galaxies, which are primarily determining their color. So to first order, when you look at the night sky and you see a red galaxy, it means it has not had any star formation recently. And if you see a blue galaxy, it means it's had a bunch of star formation. And it has young, hot stars, which are blue. Those blow up as supernova and disappear, and you're left behind with the red ones. So the same thing when you go up at the night sky and look at stars, you see a red star, it's a cool star. You see a blue star, it's a hot star. And so galaxies is actually quite similar. We're seeing starlight. And it's redshifted on top of that.
I'm wondering how much variation has been observed in dark matter halos between a portion of visible matter and dark matter. Is it fairly similar, or do we have cases where there's a dark matter halo with very little luminous matter showing the lens?
So there's a lovely correlation between how much luminous mass there is and how much dark matter there is. But we love in astronomy to measure properties for huge samples and tell you the average. So the average looks great. There's this lovely correlation. Bigger galaxy, bigger dark matter halo. But it turns out there are some big outliers. And in fact, there's been some remarkable discoveries made by a team here in Toronto of galaxies, so a team at University of Toronto led by Bob Abraham, of galaxies which are very low luminosity, very few stars, huge dark matter halos. And what's cool is because they don't follow the normal trend of most galaxies, it probably means they have an interesting history. Something happened to those galaxies during their formation which makes them different. And we like studying these extreme objects because they put constraints on our models for how galaxies evolve. So to first order, there's a great relationship between how much light you have, how much dark matter you have. But the outliers turn out to be really interesting. Yeah.
Is any further progress likely to be made on understanding dark matter and dark energy by astronomers, or is it now completely in the realm of particle physics?
Still more to be done by astronomers. I would say that on the dark matter front, the frontier is on the particle physics side. So we will continue to do a better job of fine-tuning how much dark matter there is and how it's distributed. And there's some theories of dark matter which suggest that we might be able to see the collision of dark matter particles. They might give off a photon in some cases, and so that's some models of dark matter, and we could hope to detect that. But I would say the biggest progress for dark matter is in the regime of particle physics. Dark energy, totally different story. So all of our evidence as of right now says that dark energy is consistent with this description of a cosmological constant. More space, more dark energy. But our measurements are still not as constrained as they could be. So what we're going to do in the next generation of experiments is measure exactly how much dark energy there is at different distances, going back in time. And if we measure it precisely enough, and it's not a constant, if it shows some variation, then it's some totally new physics. And so that's the goal of the next experiments, is actually to measure, for example, how much lensing you have 1 billion years ago, 2 billion years ago, 3 billion years ago, how much dark energy you have, and if it's not constant, then there's no way it's this idea of a cosmological constant. It's something that's dynamic, something that evolves, and then that's going to get the theoretical physicists super excited. So there's actually two theories of dark energy. One is this constant idea, and one is something that's dynamic, which is often called quintessence, the fifth essence. So we have 4 fundamental forces in nature: gravity, electricity and magnetism, the weak force, and the strong force. Those are the 4 forces of nature. Maybe there's a 5th. And so those theories are called quintessence theories. And they're fun theoretically, but at the moment, all the data is still consistent with just a constant, the boring explanation. Yeah.
Thank you.
With a little bit of luck, we might have run out of dark energy questions. It's like, 20 years ago, everybody asked about black holes, okay?
Yeah.
Okay. There's this theme of black and dark in astronomy. I'm not quite sure what all of that means. At any rate, on behalf of the Toronto Centre, just to keep you on track for time for next year.
Thank you very much.
And there'll be another little thing in the mail very shortly,
Thank
too.
you very
So,
much.
one more time, let's thank Laura.